About LP concentration for semiclassical quasimodes. So first I'm just going to show you a bit of motivation. So our motivation comes from the crossover between quantum mechanics and classical mechanics. So very simplistically, over in quantum mechanics we have an idea that we have stationary states to describe a physical system, have eigenfunction equation, so a Laplacian plus some kind of potential. And we interpret the eigenvalue lambda squared as the energy of a particular system. The L2 mass of U is interpreted probabilistically, so it tells you the probability of a particle being in a particular state. In direct comparison, in the more familiar classical mechanics, we have a deterministic system. So in that case, we understand motion to be described by a defined position and momentum, and we have a set of differential equations given by a Hamiltonian. So in this case, a particle moves along a trajectory. We have a rough notion that in the high energy limit, semiclassical limit, the quantum mechanics should converge into classical mechanics. So the kinds of questions I'm interested in is asking how are the eigenfunctions affected by the flow? So it pays to keep in mind this intuition here, which is we have a flow line, so we start at x0, give it an initial momentum, we have a flow line described for all time. We want to think about localized packets that sort of travel along that flow line. And at least for short time, this is a decent intuition to keep in mind. So we might expect to see some concentration if these packets can spend a long time in one particular region. So to give a couple of examples of the concentrations we might often see, first one is a very simple point concentration. So this has a very high L infinity norm, but it's very big on a very small space. So this is roughly the size of one oscillation. On the other hand, we can obtain, quite interestingly, tubular concentration. So these would concentrate typically around a periodic geodesic. So in this case, we have a very small, narrow band around the geodesic where most of the mass ends up. There are a number of ways to measure such concentrations and talk about them. And the one I've been particularly interested in is taking cross-sections. So we put a hypersurface through the eigenfunction and then look at what the LP norm of the eigenfunction when it was restricted to the hypersurface is and try and obtain some bounds. So the simplest case is the Laplacian, and the Laplacian is always the model case we use for these kind of problems. So we want to ask the question, given uj an eigenfunction, what is the size of the LP norm of uj when it's restricted to h? And we're looking for estimates of this form. We have the LP norm over here. We want some function that grows in lambda, and the growth will be dependent on n and p. And we always compare to the L2 norm of U over the full manifold. The idea being that the manifold is our universe, so we'll normalize that to 1. So questions are, firstly, what kind of F are possible? Secondly, how does the geometry of M, which is the underlying manifold, and the internal geometry of H affect the estimates? And the final one is, whenever we obtain an estimate, we want to know where it's sharp. So what are good sharp examples? Now for Laplacian eigenfunctions, work by Berkshire and Zvetkov gives us F in this case. So here we have a polynomial growth in lambda, and delta NP tells you how fast it grows. So I've plotted down here delta against 1 on P, and there are a couple of important points. The first is the L infinity norm, so that goes as lambda to the n minus 1 on 2. The L2 norm, so we can have some growth on L2 mass restricted to the hypersurface, and it can grow as much as lambda to the quarter. This is in any dimension. This lambda to the quarter is the same. Then we have the kink point. So this is actually a change in regime. When we look at sharp estimates, point-like concentrations are sharp here, and tube-like concentrations are sharp for this second part of the graph. And a lot of the work in this area is involved in determining this particular kink point where the regime changes over. So a couple of notes on their result. It's actually for a smoothed spectral cluster. So in this case, we're taking a smoothed out sum of eigenfunctions that have similar eigenvalue. So while this definitely implies the same estimate for eigenfunctions, the fact that it is sharp for clusters, and it is, doesn't imply that it is necessarily sharp for eigenfunctions, because you could have a number of eigenfunctions of a similar eigenvalue adding up to give concentration, where that might be impossible if you restrict to only one eigenvalue. The final thing to say about Berkshire-Ardens-Vetkoff is that they got better results for small p in this tube region if they're working with a curved hypersurface. I'll say a bit more on that later. So what I have been doing is trying to extend this into the semiclassical setting. And just to give you an idea of how we might go from differential operators to semiclassical operators, we'll go back to our Laplacian plus potential example. So we're just going to rearrange this equation, pull u over, divide through by lambda squared. The whole point of this is we want to encode the energy into the operator. And we set lambda inverse is equal to h, and this is the scale of the problem. And then we're going to use a method very similar to the Fourier transform method of solving a PDE. Instead of multiplication on the Fourier side going to differentiation, however, we have multiplication on the Fourier side goes to a scaled differentiation. So in this case, we would have a symbol, xi squared comes from the Laplacian term, and then a potential term. Now you can go the other way under some reasonable assumptions on p. So starting with a symbol pxi, you can do a semiclassical quantization and end up with an operator. We usually refer to these as semiclassical pseudo-differential operators. Now, in this setting, I've been able to generalize Berkshire-Ardens-Vetkoff's work to a large class of semiclassical operators. One needs to put some assumptions on p, and the assumptions on p are really assumptions on where it vanishes, because if you think on the Fourier side of this, if the symbol is non-zero, then on the Fourier side it's invertible, and we can carry that over to say that the operator we get is locally at least invertible. So we're only really worried about where the symbol is zero. Also, instead of a cluster, we look at a quasimode, so an approximate eigenfunction. We apply the operator pxhd, measure what we get in L2, and we require that it be at least order of h. So these are the assumptions we make on the symbol. So first assumption, it vanishes simply at any point that it vanishes. So we have a nice hypersurface with a well-defined normal. Secondly, we need some dispersive estimates. And the dispersive estimates that we need is require that this has a positive definite second fundamental form. So it's a very strong positive curvature assumption there. So under these assumptions on the symbol, it is able to obtain the same set of estimates as Berkshire-Ardens-Vetkoff did for the Laplacian. However, when you're working in the semiclassical setting, there's a nice division due to the geometry of the hypersurface. You can quite easily deal with trajectories that pass directly through the hypersurface. So remember, we are thinking about the trajectories having packets track along them. So if a packet tracked directly through this hypersurface, it's not going to spend very much time there at all. And that's reflected in the norm we estimate we get. We get that it's order 1, so there's no concentration at all. And this is the best we could possibly expect. At the other end of the spectrum, we have what happens if we're tracking along a trajectory that lies completely in h. Now in this case, you obviously do spend a lot of time here, and this is what gives rise to the tubular concentrations. And they have an L2 mass growth of h to the minus a quarter. So these are the two ends of the behavior that might happen for L2 concentration. And one might ask, well, what happens if it doesn't pass directly through, but it, for instance, glances off the hypersurface? This is an intermediate case. And I said I'd go back to Berkshire-Ardens-Vetkoff, and indeed, in the two-dimensional case, they were able to obtain better estimates where the hypersurface h is curved. And later, these were able to be extended to all dimensions. Now, in this case, we have a sharp example might be edge of a polar cap on spherical harmonics. So in this case, you see a great circle comes up, glances off the side of the hypersurface, carrying some energy away. In this case, the growth is lambda to the 1/6, so a little bit better than the lambda to the 1/4 that you would get on a general hypersurface. So also looked at extending these to semiclassical operators, and the property that you want to extend is this glancing property. So what do? Take a hypersurface. You have a nice defined normal nu, and then we assume that any flow line glances at this point that it meets the hypersurface, which is the same as assuming that the acceleration is non-zero. So it could have zero velocity in this direction, but so long as it's accelerating, that's all right. So in this case, we're getting things carried away from the hypersurface, and we expect better estimates. And like the Laplacian case, we are able to get those estimates, and it's h to the -1/6. Okay, the things that I'm going to be working on here. So far I've only talked about internal structure of h in terms of what you might get better estimates. One also might expect to get better estimates if you make some geometric assumptions on M, the underlying manifold. If we go back to our idea of packets tracking around these flow lines, if you have a flow that disperses the packets everywhere in a sort of even fashion, we might expect to get less concentration. So I've been looking at manifolds with negative curvature and been able to get with Hassel some improvements for estimates for LP over the whole manifold. So we haven't done restrictions bounds yet, but we've been able to obtain some logarithmic estimates in this case, and that work feeds on the earlier work of Berard, which implies the P is equal to infinity case, but his work was more focused on the counting function remainder term. So this is something I would like to look at further. Second, I'd really like to have a look at manifolds with boundary. So far, dealt with manifolds that have not got a boundary or where we can avoid the boundary. The boundary can cause all kinds of trouble, and there is known to be examples such as whispering gallery modes, which have quite significant concentration. So I'd like to be able to obtain some estimates for manifolds with boundary and take into account that. The final thing is look at hypersurfaces that are not fixed. That is, when I set a hypersurface, I set it down, I allow h to change, but the hypersurface itself remains fixed. So particularly with something like a manifold with boundary, it might be interesting to say, let's consider all hypersurfaces that are a fixed distance from the boundary, and we want that fixed distance to depend on h, and see what kind of dispersion you get on them as h goes to 0. So these are the 3 problems that I'm most interested in looking at over the next year. I think this might be a good time to stop.